Hello and welcome to Aerotech's Automation1 Motion Control Platform educational series. Aerotech is a company that solves your toughest precision motion and automation challenges. Automation1 is a motion control platform consisting of software-based controls and development tools, PC and drive-based control hardware, and hardware-based drives for servo motors and other devices. In this video, we will take a look at using the analog and digital I/O of Automation1 drives. My name is Chris Charlesworth and I am the European Control Systems Engineer for Aerotech. To begin, we'll have a look at Automation1's standard I/O options. We'll begin with the general specification and then we'll take a look at the different quantity of I/O by drive type. We'll begin with the general specifications. Every drive has different options available, so these are just generally across the whole product range. Digital inputs can be sourcing or syncing in type. You change the wiring depending on which one you want to have, and they are generally 5 to 24 volts DC. Digital outputs, again, can be sourcing or syncing depending on wiring, 5 to 24 volts with a maximum output of 250 milliamps. Where we have high-speed digital inputs, they're generally a differential input of 5 to 24 volts, and the high-speed outputs, these are on the XR3 and iXR3 only, have an output rate of up to 32 MHz. Analog inputs, 16-bit is the resolution, 0 to 10 volt signals, and they can be single-ended or differential. Analog outputs, again, 16-bit resolution, 0 to 10 volt signals again, and 5 milliamps maximum current. You should always confirm the specification for these inside the drive hardware manual. Inside the manual, you will also find all of the wiring information that you will need to be able to implement these in your system. So, let's take a look at the I/O quantity by drive type. We'll begin by looking and considering the iXC2, the XC2, and the XC2E and iXC2E, along with the linear variation, the XL2E. As standard, this has no extra analog and digital I/O. The EB1 option will add 1 analog input, 1 analog output, and 8 digital inputs and 8 digital outputs. The next series of drives, sort of the next size up if you will, made up of variations of the XC4, the XL5E, and the XL6E, each have 1 analog input and output, and 4 digital input and output. These, however, are used as part of the limit switches as well, so generally speaking, a system will have only 1 or 2 available. Again, check the hardware manual for details. When we add the expansion board option, we have 4 analog inputs, 4 analog outputs, and a total of 20 digital inputs and 20 digital outputs. When we move on to looking at the SI4, so this is our stepper interface drive, you can have up to 8 digital inputs and 8 digital outputs, but there's no analog option. Looking at the XI4 and GI4, 4 analog inputs, 2 analog outputs, along with 9 digital inputs and 8 digital outputs. These are interface drives, so the XI4 is for interfacing in a closed-loop manner with external servo amplifiers or stepper motors. The GI4 is our interface drive that's used to talk to third-party Galvo controllers. We then have the XL4S and the GL4. These are our voice coil drive and our Galvo scanhead drive. 1 analog input, 2 analog outputs, and then 4 each of digital inputs and digital outputs. And finally, we look at the XR3. So the XR3 and iXR3, this is our up to 6-axis drive rack. The analog inputs and outputs are 2 per axis, so that's included in the control card of each axis. And then it has a general 16 inputs and up to 28 digital outputs. 12 of these outputs are high speed, and you will find that it's 2 per axis. This allows you to echo out things like encoder position. Now we'll move on to how to use the different I/O on the drives. We'll begin looking at the digital I/O. We'll look at the basic, how to set, and how to get the data from the digital inputs and outputs. Let's take a look at using the I/O within an actual program. We'll begin with the digital input, and we'll take the value from the digital input and read it into an AeroScript variable. Now, we'll begin with var, and then we'll put in our variable name, which in this case will be my digital input. And we're going to define this one as an integer. All digital inputs and outputs would need to be defined as integers for the purpose of bringing them in and out of a program. So as an integer, and then we're going to read in to that variable, so my digital input is equal to, and then the first command is digital input get. Now we define the axis we want, and then we also define which of the digital inputs. So in this case we'll have digital input 0. There we are. That's a very simple one line to read in the variable. Now we can also do the same thing for reading the status of a digital output. So we'll start with defining that variable, my digital output. We will then set digital output, and we'll do, in this case, digital output get. Now, I don't know about you, but I don't like writing full commands if I don't have to, so I've written dig, and I can already see on the IntelliSense list, I can select it and hit enter, and that will then fill in for me. I can open my bracket, and it's already put the close bracket in, and then I just have to define the axis and which of the digital outputs we're going to set. Nice and simple. And finally, we will set a digital output. So, digital output set is the command. Select our axis, select which one we want to do. Let's do number 7 in this case, and then we'll set it to 1. In other words, turning it on. So it's as easy as that. We'll build the program. If you were watching carefully, you'll have seen that there were no errors at all before this was built. We'll hit play, and then on the right hand side of the screen, we'll see axis X bit 1 output has been set to on, and so has bit 7. Bit 1 was already on from earlier. So on the right hand side, you can see this variables and IO tab, and we have different items that we can see from here. The variables and IO show you all the inputs and outputs for each drive. So you can see down at the bottom here we also have the analogs. Another thing you can do with digital inputs is trigger faults. Now to set this up is very simple. We go to the configure workspace, and then we go to the protection part of the configure workspace under the axis that we're looking to configure. Now inside of here, near the top under the inputs, you can see we have an emergency stop fault input, an external fault analog input, and external fault digital input. So you can set these to one of the inputs that is on the drive, or you can leave it as the dedicated input in case of the emergency stop. So you can see on digital inputs here, we can set it to any of them. And then to configure this, we would look at the fault mask, and then we would allow the external fault, and we would indicate it like so, and then save the parameter. Now that we've looked at the digital I/O, we'll move on to look at the analog. Now, as well as the basic use, it's also worth mentioning that the input update rate for the analog is 20 kHz, and each analog input can also have a filter assigned to it. We'll take a quick look at setting up analog filters. So on the configure workspace of Automation1 Studio, under the axis section, we go to I/O. Then on the right hand side, you'll see analog inputs where we can tweak the offset voltages, and we can also set up the analog input filters. Each analog input can have 2 second order digital filters assigned to it. So you can see here, input 0, filter 0, input 0, filter 1. By default, they have a cutoff frequency at 250 Hz. You can also put in lead lag, notch, or resonant filters. Now, let's take a look at actually using analog inputs. So we'll move over to the develop workspace, and then we'll add in a couple of extra lines, and we'll start by getting the value of an analog input. Now, similar to before, we will set up a variable where we will write the information into. Start off with $1. Now in this case, we will set it to be a real. These are of course floating point numbers, so we use the real data type. And then we will move on to getting the analog input value. So analog input get, you can see it's come straight up onto the screen. We'll get the x1, get the 0, and we can see it's filled in automatically for us. Similarly, we can also get the value of the analog output. So we'll do that in a very similar way. In this case, we'll once again just copy it quickly. My analog output. And then we'll go analog output get x, 0, and you can see the brackets are filling in automatically as they've done previously. And then we'll also look at setting an analog output. In this case, analog output set. Define the axis, choose which of the outputs, and then we'll set it to a number. Let's do 1.234. And it is as easy as that. So we'll just play this. The build and save's automatic. And then if we scroll down, we can see here that the channel has been set to 1.234. So there we go. Nice and simple. That's it for the analog basics. Let's have a look at a couple of the more advanced features. This will include sending analog output commands from the drive array, and also setting the analog output to track a variable associated with an axis or with multiple axes with the tracking features. Setting the analog output from the drive array. Now, this can be very useful if in your process you needed to be able to set a series of different analog output values that were going to be changed quite rapidly. And it may well be that it's due to different parts of your program needing different values to output. The beauty of this is that it can be connected to the position synchronized output function, which allows you to do some fairly complex things. So we'll set an analog from the drive array. Now, again, we try to make this as simple as possible at Aerotech. So when we start typing in analog output, you can see in the IntelliSense lots of different options come up. So we can set it to default mode, we can set it to axis and vector tracking mode, which we'll discuss in a moment, but we can also set it to the array mode. And you can see the IntelliSense has also opened the help tooltip to help you to understand what's going to happen. Let's hit an enter, and then we'll actually configure this for use. We'll use the x-axis, we'll use output 0 as we've used previously. What that update event is going to be is something that we can define. Now, this is an enum. I'll be covering enums in another video. In this particular case, we're going to look for the analog output update event, and then I'm going to hit stop, and then you can see we have three options. We could link it to a PSO event, we could link it to the PSO output, or we could link it to time and it be done at a specific rate. In this particular case, we'll just set it to the PSO output. The next part is we have to say where in the drive array are our values stored. For the sake of argument, we'll say that the first one is going to be at position 10,000. And then how many points need to be used? How many points are we going to read? Let's read 100 in this case. And then do we want it to use every event, or every 4 events, or every 5 events? That's what the divisor will allow you to do. In this case, we'll go for every event, so we'll set it to 1. And then do we want it to start over, so make it loop round? In this case, we'll say yes. This is going to be a cyclical program. So there we go. Now, once we hit enter and run this, that would allow the analog output to be set directly from the drive array and be tied to a PSO event. And that would begin immediately. So you could put this into your process code, or you could just put this into a main program that was controlling the system as a whole. Now, we'll take a look at the tracking mode. The tracking mode is very useful. There are two options for this. The first tracking mode is a pure axis tracking mode, and the second option is a vector tracking mode. This is very, very useful if you have a system where you need to know how fast an axis is going to link into an external system. So it might be running into a laser system, so you know where you are, and you're not using a laser that Aerotech is providing. So in this case, we will configure the analog output tracking mode. So once again, we start with analog output. Already we can see a list has been populating, and we can see that the axis tracking mode is on the list, so we'll just hit enter. We'll open the bracket, we'll select the x-axis again. We'll say it's going to be an output 0. Obviously you wouldn't do this all in one program, as I've now set this particular output 3 different times. And then we're going to select the tracking item. Now in this particular case, I've just typed in tracking item and hit the down arrow key on my keyboard. That allows me to select it. So I didn't even have to type in analog output axis, I just typed in tracking item. I know it's the tracking item because in the tooltip we can see $tracking item as analog output axis tracking item. That means you're going to use the enum. And then we can choose what we want to run from. So the acceleration command, current command, piezo. In this particular case, we're going to use the velocity feedback, and we're just going to hit enter. We're going to put it in a scale factor. Now it may well be you need to shrink this down to fit. So we'll say 0.1. In this case, we won't have an offset. What's the minimum voltage going to be? So we'll say -10. And what's the maximum voltage be? We'll say +10. So it's a full scale. Now, there are full instructions inside the help file for how to set this up and what each of the different functions will do. With the vector tracking mode, it's also very similar. Once again, we'll start with setting up vector tracking. We'll choose our usual x-axis and 0. Now you can see here we have multiple axes that can be selected. So we'll open up an array, we'll put x and rx in there. If you wanted to, you could actually put a variable in there. So if in another part of the program you've defined a variable, you can put that in there as well. And then we're going to choose the vector tracking item. And again, we'll, in this particular case, use the position feedback. And then we have the same settings as the previous one, so set a scale factor, set the offset, set the minimum voltage, and the maximum voltage. Nice and easy. This would update at 1 kHz. There we go. That's an overview of the advanced tools that you can use with the analog I/O inside Automation1. That concludes this Automation1 educational video. Thank you for watching. I hope you enjoyed learning about the analog and digital I/O of Automation1 drives and understand the specification and how they can be used within controller programs.